Yeah, could I just ask some people in the back who want to watch this talk? I was taking a look this morning and you really can't see the slides back there, so there's lots of space in the front. Maybe take a minute to come a bit closer. Like, however big I make the font, you will not see it. Make some new friends, you know?
So if the last talk was about how do we improve Rust type system to verify more things, this talk is about how we're going to use Rust existing type system to improve program synthesis of Rust programs. And our speaker will be Jonas.
Thank you. Yeah, so this is talk leveraging Rust types for program synthesis. And it's joint work with all of the lovely people you see there on the slide. So I'll start the talk with Rust. And I mean, as we just saw, Rust has this very fancy and nice type system, right? Well, but if you're starting out, if you're a beginner Rust programmer, this is what notoriously makes it also difficult to use. So if we take such a beginner Rust programmer, this is how I imagine the experience is. And here the crab is representing the Rust borrows checker. But our question is, since programmers already have to write all of these fancy Rust types, can't we just leverage them and actually get the code almost for free? Well, our work does exactly that. And given a Rust type and some lightweight functional specification, our tool, which we call Russell, will generate Rust code. And this isn't just any Rust code. We want Rust code with some guarantees, namely that the Rust code will be well typed and that it will provably satisfy whatever functional specification the user wrote. And in the rest of this talk, I'll spend the time to describe to you how we turn this foe of a Rust borrow checker into a friend to help us guide program synthesis. I'll start with a live demo, wish me luck. Then I'll dive into our main technical contribution, synthetic ownership logic, or SOL. And then I'll finish things with an evaluation. For the demo, I'll show how Russell can help me implement some operations over linked lists. And here is a simple definition of a linked list in Rust. I'll first go over the definition a bit. We can see that here we have a sum type with two variants. The first variant is just the empty list with no fields. And then the second variant is a cons node which has two fields. First, generic payload T, and then a pointer with ownership over the rest of the list. Let me switch now to the live demo. So hopefully you should all see, it's quite big, but okay. Yeah, hopefully you should all see this type definition that I just showed in the slides. Here we have our linked list, and the first example I'll show for the demo is this singleton function, which takes an element T, and we want our synthesis tool to return an implementation which allocates a singleton linked list. Now, if I run synthesis for this, we'll see we actually get back the expected implementation. And that's pretty cool. You might be a bit surprised here, right? Why doesn't it just return an empty list? That might be simpler. Well, here the tool is able to notice, and it's able to leverage the linear type system in Rust, and it can notice that we're passing in this element T as an argument. And since we have the linear types, if we don't end up using this element, then we would have to drop it. And probably the programmer doesn't want this, so the tool can avoid that and actually make use of it and return a singleton list. Okay, that was a pretty cool example where we don't have any specification at all, just the signature. But in the general case, the user will have to provide probably some lightweight specification. And to enable that, we allow the user to write pure functions. So here this function isn't synthesized. The user wrote a length function to calculate the length of a linked list, and they've annotated it as pure. It's not mutating the list. It's kind of a measure over the data type. And for our next example, we'll take a look at this peek function, which takes a shared reference to the list and returns a reference to the head of the list. You might notice that from our type definition up here, if we get a nil list as the argument, then this isn't solvable. There's no T that we could add return a reference to. And so the programmer here has also written a precondition requiring that the length of the list is at least 1. And this way, if we now run the tool on this example, then we'll get back an implementation where the tool is actually able to notice that in the nil case, this has violated the precondition, and so it's unreachable. And in the cons case, it has the correct implementation where it's returning the reference to the head. And for our third example, we'll be taking a look at the push, where now the signature is taking a mutable reference to a linked list and a new element that we want to push to the linked list. And here I've written a post condition which states that the linked list after the function call, the length of this linked list should be 1 greater than it was before the function call. So here the hat means after the function call, the star is dereferencing the list before. And if we run our tool on this function, then we actually get back the implementation which is pushing to the list. So here it's actually a recursive implementation. So if it encounters a cons, then it recurses further until it reaches the tail of the list, then allocates a singleton list and writes that into the tail pointer. Some of you who might be a bit more experienced with functional languages might be a bit surprised that here we're getting a recursive implementation, but actually this has good reasons in Rust. And maybe, I don't have time to cover this, but maybe if you're interested, then ask me a question after the talk. Now I'll switch back to the slides. Okay. So this is what we just saw in the demo. Here, Russell takes this left-hand side as input and produces the function implementation as output. But how does the synthesis actually work? Well, Russell is a deductive synthesizer, meaning that it searches for a correctness proof for a given specification. And then from that proof, it extracts a program. So more concretely for us, it takes this Rust type and functional specification that the user provided and turns it into a synthesis goal. This is a pre and post condition, and then it searches for a proof derivation which satisfies the whole triple. And from this derivation, it extracts a program. And at the heart of every deductive synthesizer is a program logic, which is used to construct the proof derivations. For us, this is called SOL, and it's the main technical contribution of the paper. At this point, you might be asking, why are we even coming up with some new program logic? Aren't there already lots of them out there? Can't we just reuse an existing one? Well, there are, but the answer is that none of them actually satisfy all of the properties that we need. Namely, we need a program logic that's friendly to program synthesis. For this, we can draw inspiration from previous work for program synthesis with separation logic specifications. But for us, we want the user to be able to specify the properties at the source code, at the level of the Rust, where the previous work requires them to write the specifications in separation logic. So here we need to draw inspiration from existing verifiers for Rust, such as Prousty, Crusoe, or now Flux, where they allow the user to specify functional properties at the level of the Rust program. But this still isn't enough, because all of these verifiers, they assume that the code has already gone through the borrow checker. Whereas for us, the borrow checker is not in the picture. We need to have a logic that ensures that our program will be correct. And so for this, we can draw inspiration from Aeneas, which has its borrowing logic, and there it ensures that generated programs will be type correct. We can combine all three of these aspects into our synthetic ownership logic, or SOL. Now, SOL is a Hoare logic, or more specifically a separation logic, which means it's judgments of the familiar Hoare triples. They have a precondition, a program, and a postcondition. And in this example that I'm showing on the slide, it's a SOL rule that defines the semantics of the cons constructor for linked lists. So this rule says that if we have a heap that contains an element of type T and a box, then we can execute the cons and get back a list. If we take a look at how we can use these rules like this, like the one that I just showed you, to derive the singleton example, then first the tool starts by taking this signature that the user provided. It then generates the precondition and postcondition automatically. And the general approach is that it will apply SOL rules either forwards or backwards. So it will either match the precondition or the postcondition and apply the rule. In this example, we can see that there's a list in the postcondition, and the rule that we just saw has a list in its postcondition as well. So we can match those two up, apply the rule backwards, like so, and then we get rid of the list in the postcondition, replace it with its two fields. We can repeat, we have a rule for a box constructor. This replaces the box in the post condition with a list that it points to. And then lastly, we can apply the other rule for lists, which is this nil constructor. This gets rid of the list in the post condition and leaves us with just the element. Now the tool notices that the precondition and post condition match up, and so it can return this as a solution. Of course, sometimes the synthesizer will have a choice of what rule it can apply. So this is the derivation path that we took with the rules here. But there were also some alternative choices that it could have made. So the synthesizer under the hood will actually perform a backtracking search. However, the nice thing here is that unlike for previous tools, the Rust type system will drastically restrict the search space, and so we're able to find much larger programs much faster. Now I'll go on to the evaluation. Here we wanted to check that our tool is actually doing what we said, namely that it's generating Rust programs that are well typed, and also programs that satisfy the specification. So we took 3 sources of Rust programs. First, we took a look at Rust programs in the wild. So we took a look at some Stack Overflow questions where beginner programmers were struggling to implement Rust functions. Then we also took some examples from the linked list tutorial for Rust. And we took all of these, took the signatures for them and added annotations. Then for the second source, we took examples from the previous work for deductive synthesis using separation logic and translated that into Rust signatures. And lastly, we just took some examples from benchmarks of verifiers which already came annotated and just took the signatures from those. And overall, from all 3 of these sources, we were able to get 117 function signatures with annotations. And our tool, Rasol, was able to solve 115 of those. For the 2 that it failed, one was it was unable to solve because the implementation actually required unsafe Rust code, which the tool is not able to synthesize. And then the second one was due to Rasol's inability to synthesize pure arithmetic expressions, which is not the focus of our work. Of these 115 synthesized functions, they were 5.4 lines of code on average. And when we took a look by manually inspecting all 115, all of them had correct implementations, and we then took those implementations, ran them through a Rust verifier to actually check that they satisfy whatever specification they had as well. I just want to point out that even though we have 5.4 lines of code here on average, some of the synthesized functions were rather non-trivial, such as, you don't need to read the code here, but this is a rose tree flattening function, which actually requires the synthesis tool to come up with 2 auxiliary functions. The implementation is 24 lines of code long, and it took about 10 seconds to synthesize. And this example, actually, it wasn't possible to solve with the previous work for deductive synthesis with separation logic, and we believe that that's due to the pruning that the Rust type system allows us to do. Then, as you might remember, at the start of the talk, I said we also want to guarantee that our return programs will be type correct. And to do this, we just wanted to gather as many functionals, or like function signatures. And so we just took a look at the top 100 crates, extracted the function signatures from those crates without the body. Of course, these were not annotated, but this let us get quite a few signatures. We had to filter out some which used vectors or row pointers, which we don't support. And overall, this let us synthesize about 3,000 lines of code, all of which were well typed when we ran them through the Rust compiler. Of course, some of these were rather trivial, some just returning an integer, then the tool can just return a default value. But surprisingly to us, maybe, was that we actually got some implementations which matched the library implementations in the crates. Okay, so that's everything from the talk. I just want to summarize that in the talk we saw 2 main points. We saw our tool called Rasol, which is the first deductive synthesis tool for Rust, which leverages Rust types to reduce the specification overhead. And then we saw our main technical contribution, sol, which verifies well-typed programs which satisfy specification and leverages Rust types to prune the search space, as well as being friendly to synthesis. Here, the QR code will take you to an online demo. It looks a bit like this if you want to try it out. And then if you want to run the tool for it, you can click under Tools and Rust Sol. Okay, that's everything if there are any questions.
Hi, I'm Technion from Purdue University. Nice talk. My question is, in your pig example, is the precondition actually necessary? Because I feel like if you can exploit parametricity, you can derive the same conclusion, right? Like in the new case, you can actually derive anything in T.
So you could use that, I guess. You could see the tool, if I remove the precondition, it will say that it's unsolvable. And so it could see, okay, in this case it's unsolvable, so I'll just give up and say it's unreachable. But for us, we wanted to have this guarantee that it's satisfying the specification. And for that, you can't just kind of arbitrarily panic. But yeah, you could use that as a heuristic.
Thank you.
It would rely that the rules are complete, I guess.
Hi, Tim Princeton. I was wondering about how the tool decides which of the possible options after it does this backtracking search to return. Like, what heuristics do you use to decide?
So in general, it will just return the first solution that it finds. It's just that, yeah, in the example that we saw, the first solution finds is really this singleton list. It will avoid trying to drop something if it can. So we just guide it based on that. We don't have any guarantees, but generally this will be some simple solution.
So will the system ever try to copy or clone things, or is it going to also prefer not to make copies or clones?
So it can copy things, that's fine. For clone, that's just a regular function. And for this, we allow the user to kind of provide external functions that the tool can call. And so if you provide a clone, then it can do that. It will add extra lines of code. So if it can find a shorter solution without cloning, then it will do that. If it needs to clone, then it would clone.
Thanks.
Yeah.
Just a quick question about the program logics in which you're embedded. I noticed that you needed a pure annotation on a function that takes in immutable references and therefore can only be pure. Is that a limitation of the logics you're building on? Is that optional? What's the role of that?
So I would say, yeah, this pure annotation, you could quite easily infer it and just lift the restriction. This I just took from existing verification tools, which have also require the user to specify this pure thing. It's just from existing tools, but okay. You could remove it.
Hi, I'm Russell from UIUC. So a lot of real-world programs in Rust use a lot of the standard libraries collections, such as like vector and hash map and that kind of thing. I'm wondering what would have to be added to the system to support those collections, because if I remember correctly, you said that programs that include like vec, for example, couldn't be synthesized. Am I remembering that correctly? Mm-hmm.
Yeah, so the main challenge with supporting vector is that usually kind of the tool doesn't really have any issue with supporting it. It's just you need the constructs to work with it. And the tool currently isn't able to come up with some auxiliary thing. So generally, if you have a vector, you want to have a while loop, which will maybe be accumulating something on the side, and the tool isn't able to come up with this auxiliary thing to accumulate on the side. So I think in theory it should be possible to support it. You just need the extra machinery to kind of give the rules to the tool to be able to come up with whatever it needs.
So there's not too much like a theoretical boundary to it. It's more of an engineering effort.
I think so, yeah.
Okay. Thank you.
Do we have time for one more question?
Just real quick.
It's quick. John Hughes-Almage. So in your push example, why did the tool generate a recursive program that appended the element to the end of the list instead of just conning it all at the beginning? That would surely have been simpler.
Yeah, so to put it at the beginning, the tool would need to take this mutable reference to a list and turn it into an own reference, which it can then put in a box to put in the tail. And it can't, in safe Rust, you can't really take a mutable reference and turn it into an own thing. What you could do is that the standard library provides this wrapper function around a short piece of unsafe code, which kind of hot swaps something in. And if you provided this to the tool that it would be allowed to call it, then it would be able to just say, swap in just an empty list, give me back ownership over whatever was there. I'll construct the extra list at the head of it, and then write that back in to replace the nil list that I put in. So it would be able to solve it, it's just we didn't provide it the standard library function around the unsafe code.